All right, let's talk about light. For centuries, we've known it delivers energy. You can feel it from the sun, right? But can it also push things? Today, we're diving into the incredible experiment that proved light isn't just a wave. It can act like a tiny physical object. So let's start with this really fundamental question. We know light comes in these little packets of energy called photons. But do those packets have momentum? I mean, can a photon actually hit something and knock it out of the way, just like one billiard ball smacking into another?
To figure this out, we've got to go back to the early 1900s. Physicists at the time had a pretty good handle on things. But there was this one nagging question, a critical piece of the puzzle that was still missing.
See, thanks to Robert Millikan's amazing work, we already knew that photons carry energy. And he proved that the amount of energy depends on the light's frequency, its color, not how bright it is. But that left a huge question just hanging in the air. Can light actually push stuff? Does it have momentum? Millikan's experiment, as brilliant as it was, just couldn't tell us. And that's where our hero, Arthur Compton, comes into the story. In 1923, he came up with this absolutely brilliant idea to settle the debate for good. This was his whole thought process, right here. Compton basically said, look, if these photons are really particles and not just some abstract energy wave, then they should act like particles. And what do particles do? They collide. They should be able to physically hit an electron and transfer momentum, just like in a game of pool. Now, to test this, he couldn't just use a regular old flashlight. No, he needed something with some serious punch. So he chose X-rays. Why? Well, because X-ray photons are absolutely packed with energy. They're so powerful that if one hit an electron, the collision would be dramatic enough to actually see and, most importantly, to measure. So the stage was set. Compton had his high-energy X-ray photons, and he had his target electrons. What happened next was one of the single most important collisions in the entire history of science. Let's just walk through exactly what happened. Kind of like an instant replay. First, you've got this high-energy X-ray photon, zooming toward an electron just sitting there. Then, bam! Impact. The photon slams into the electron, sending it flying. But here is the critical part. The photon itself doesn't just disappear. It bounces off, scattering in a new direction. And it's changed. It lost some of its energy in that collision. That little bounce, that loss of energy, that was so much more than just an interesting result. It was the smoking gun. It was the definitive proof of light's secret identity. And this whole phenomenon naturally got a name, the Compton effect. It's that measurable drop in a photon's energy, which means his wavelength gets longer after it smacks into an electron. This is the discovery that won him the Nobel Prize, and for very good reason. This table here lays out the evidence just perfectly. Before the collision, the photon has high energy. In the world of light, that means it has a short, tight wavelength. You can think of it like a high-energy color, like blue. But after the collision, its energy is lower, and that loss of energy makes its wavelength literally stretch out and get longer. It's as if it shifted towards the red end of the spectrum, the low-energy end. And this is the absolute key to everything. A pure wave just couldn't do this. A wave would sort of wash over the electron, maybe make it wiggle a bit, but it wouldn't have this clean, one-on-one billiard ball-style collision, this very specific kind of direct impact, this transfer of momentum. That is something only a particle can do. Compton had proven it. Case closed. Okay, so a tiny particle hit another tiny particle almost 100 years ago. Big deal, right? Why does this matter so much to us today? Well, it turns out it's a huge deal. The impact of this discovery is, and I mean this literally, everywhere. Anytime you get a medical X-ray, the way those X-rays scatter to create the image is all thanks to the Compton effect. It's the foundation for understanding what happens in giant particle accelerators. Even something like a solar panel turning sunlight into electricity, that relies on this exact interaction. And the behavior of electrons inside the chips that power our phones, our computers, all the AI stuff, that's all governed by these very same quantum rules. So let's just bring it all home. It really all boils down to these two pillars of proof. First, Millikan came along and showed us that photons carry energy. But it was Compton who delivered the final knockout punch. He proved that photons also carry momentum. And with those two pieces together, the picture was complete. Light, without a doubt, behaves like a particle. And that leaves us with one last, kind of mind-bending idea to chew on. Compton's experiment helps show us that light lives this strange double life. It's both a wave and a particle. But it really makes you wonder, doesn't it? If something as mysterious and intangible as light has a secret particle identity, what else out there in the universe does too?